Our next guest is Carsten Riggelsen, Head of Data and AI DACH at AllCloud. Dr. Carsten Riggelsen began his career in the data and AI realm before these topics were known to a wider audience, and before they were mature enough for cross-vertical industry adoption as we see today. We are very pleased to have him with us today to talk about machine learning in manufacturing and how it can improve your production and quality assurance. Carsten, thank you for joining us today. The stage is yours.
Thank you very much. I'm going to share my slides. Hope that this works. Are you seeing my slides now?
So yes, we can see your slides.
Okay, good. That makes me very happy. It's always an adventure. All right, so thank you very much for the introduction. Very kind of you. Hello, everybody. Hope you're all fine during these times. So indeed, my name is Carsten Riggelsen. I'm in charge of data and machine learning, but also AI and edge computing and IoT across DACH for a company called AllCloud. We're a professional service company. And I'm going to sketch a few things pertaining to machine learning in manufacturing by way of a couple of use cases, and we'll spice it up with a couple of opinions and a couple of sentiments throughout. So it will not only be about manufacturing. So a few words on the company that I'm working for and at. As I said, it's called AllCloud. We are a professional services company. So even though I am in charge of everything that pertains to data, that still belongs to the innovation bucket these days. Not many companies actually industrialize it or scale data-driven use cases, including machine learning and AI. So what we are doing and what we have observed is that many companies that really they lack the very foundation to actually to work on these things on a scaled fashion. So we also embark on cloud enablement for companies, cloud transformation, cloud modernization, and we even managed service providers. So once you have moved something to the cloud, we are also able to maintain it for you and run operations, including the machine learning workloads that you may have, right? So it's very important to state that, because most companies, they remain on this POC state with the machine learning and AI initiatives. So we are full stack and beyond, and we believe that cloud is one of the prerequisites in order to be successful for anything that pertains to data, including IoT, machine learning, and AI. So we are a global company. We are present in DACH, in Munich, Berlin, and Vienna. We are all in AWS. We are one of a very select or one elite group of partners that have a very, very close and strategic relationship with AWS. Only a handful has that. And this is, of course, underpinned by the fact that we are very well certified across all aspects pertaining to AWS Cloud. We have a bunch of cloud experts, obviously, and we're able to cover, most themes pertaining to cloud, from migration across pretty much all topics to software as a service. And also, as one of only select few partners, we actually are machine learning. We have the machine learning competency. You see that down left as well. So that's basically AllCloud in a nutshell. And I'm here today to basically present the innovation part of AllCloud, so machine learning, AI, and everything that pertains to data. Right. So manufacturing use case, of course, I mean, you can pretty much there are opportunities across the whole value chain, you could say, when it comes to manufacturing and digitization, not only when we talk about data. So of course, the low-hanging fruit as I want to visualize something in my factory. So buzzword is here, smart factory, and you have a lot of sensors connected to your production equipment and production lines, and that's what you see down right. So data visualization is one. Does not necessarily have to do with data or machine learning as such, but nevertheless, it's a low-hanging fruit. Many companies are not even there. Of course, you also can talk about general new business models such as machine as a service. That's a much broader topic, and that goes beyond just being a data thing. right? You also have digital twins, where you can basically experiment on a shadow of some kind of asset that you may have in your factory, right? You can even talk about, I mean, human resources for the factory workers, obviously, right? So there are a lot of data-driven use cases, in particular there, where you already, in one way or another, are collecting data in some automation process. You might be able to use the data that comes about in a new way, because it's only been basically used there for one single purpose. When there's already automation in the game, so to speak, you might be able to use the data in a different fashion and actually gain more insight and predictive power than you do now. Today, as I said, not today, I didn't say that. Today, manufacturing use case, I'm focused on one particular use case or theme of use cases, namely quality control via computer vision. And why do I say computer vision? Well, first of all, computer vision kind of speaks to the intuition of everybody when we talk about machine learning and AI, right? So we think about, autonomous driving, face recognition. So there are technical terms for those things called image classification, object detection, localization, and segmentation. And when it comes to quality control, it's always about figuring out where or what kind of product is in one way or another faulty. And if you look at it from an optical point of view, you're able to detect it, right? So this is one modality. Of course, sometimes that's not enough. Sometimes you also need, you need the haptic perspective as well to figure out whether something is broken or not, or something has a particular quality or not. But of course, computer vision is usually one way of going about that, and it's very successful way of doing this. So this is why I focused on computer vision for quality control, as I said, even though there might be other ways of going about this as well. So I'm going to talk about the two particular use cases we are working for with customers. One use case is fairly elaborate and absolutely non-trivial because it also involves installing hardware next to the data science and machine learning part. And the other use case I'm going to talk about is not about hardware. There the data was already present in the production line. But there the model then, on the other hand, we developed was then much easier to develop, right? So these are the two use cases I'm going to briefly talk about today. So the first use case is for an international company, a textile fabric production company. A fairly conservative, I wouldn't say really modern company. They are hardly digitized. They were embarking on a cloud journey. They want to move to the cloud. And while doing so, they wanted to embrace new methods for quality control. It's always easy, obviously, when you start from greenfield, rather when you have to move something on-prem to the cloud first, and then also do the data science and machine learning, right? So here, they basically did both of the things. So they moved to the cloud while we were also engaging with them on quality control for this particular case here. So the challenge is here to detect flaws in the weaving. The goal is to reduce manual quality control efforts. At the time being, or a couple of months back, people were manually subsampling, so looking every 10 minutes, more or less at random at fabric to figure out whether there was a weaving error or not. Provided that there was a weaving error, then the whole batch was basically discarded. So several meters from where the weaving error was basically discarded. So it was very labor intensive and was more or less ad hoc. So it was absolutely not optimal. And at the end of the day, the goal is here, as I said, to reduce manual quality control efforts, but also to reduce number of flawed products from actually leaving the factory, right? Because of course there's a lot of products there where the quality was actually bad and left the factory floor because it was simply not detected, because it was a very laborious effort to do so. The approach was here, as I also mentioned for this use case here, is that we also embarked on developing the hardware for attacking this problem here. So there was really no way of we didn't have any data before we attacked this particular use case here. And of course, then using the data we then obtained to develop a machine learning model that was able to do quality control in a more systematic and sustainable way than just manual intervention. So for the actual hardware development, we actually relied on, well, Raspberry Pi. Sorry for bringing across the nerd in me, but nevertheless, that's the Raspberry Pi. That's what you see to the left here. We installed some an Edge runtime on there, Greengrass, and we put it in a cage. And that basically means that we were then able to, at least for the particular training phase, for machine learning, we were able to feed that particular box you see to the left here manually with some fabric samples here in order to collect some samples. So that's what you see the lady in the middle is doing there. So she actually pushed that through the machine there. Of course, later on in production, this is scale, and this is what we're doing now. So actually in the production line, this is much more professional. But nevertheless, for the R&D initial phase, this is how it looks. So the data collection in the middle there. The woman then, of course, then has to label those particular items that she scans as being, faulty or correct. That's what you see to the right there. For instance, there's apparently a faulty segment there, the red one there. You can hardly see that with, just by looking at it. But of course, she's highly skilled, that woman there, and she actually also uses haptics, and she actually stretches the fabric to actually to establish the fact that there was an error there. The green ones there are 3 patches that are fine. So in that way, we are able then to collect samples, which we then use for machine learning model to actually train a model, right? One example or one exciting one question we had here was, of course, can we by merely looking at it from a visual point of view actually distinguish whether the fabric is okay or not, right? As I said, the woman herself, she actually also stretches this and she touches this. But of course, we can't do so. At least our Raspberry Pi didn't have any sensor for doing that. So we relied here 100% on the optics and on visual inspection here. So the question is, can we then, based on those example here, distinguish faulty versus correct, right? And this is already brings me to a thing we see quite often, and I think that's often underestimated when people embark on machine learning, artificial intelligence. And I like that it's really an iterative endeavor. It's very research and development intensive, absolutely non-trivial. Because the question is upfront, do we have enough data? What does the data look like? Which algorithm should I use? And in the case which you saw, which hardware should I use? How do I connect it all together? There's basically no blueprint for that. There are some best practices and processes you might rely on, but nevertheless, it is an iterative process, and it takes some patience, and you might actually fail just in real research. And I think that's sometimes forgotten when people talk about general machine learning and AI. It is an iterative endeavor, and it does take time, and it does cost a lot of effort. But that, of course, also means that the substrate on which you do your experimentation, if you just now put aside the hardware point of view, for instance, for model building and for scaling and so on, you need a platform, you need an ecosystem where you're able to experiment with all these things, right? You should be able to spin up something, an instance, so a cluster very fast. You should be able to tear it all down if it doesn't fulfill your expectations. You should be able to somehow to rely on various, cloud services if you somehow think that they will somehow help, your problem or not, right? So basically, you should rely on I would almost say a Lego building brick set where you're able to put things together in a very agile and ad hoc fashion, or a principled fashion, of course, not ad hoc, right? This is what you see to the right here, right? So this is eventually what comes out of such an R&D phase here. You have all these small building blocks here. These ones are from AWS because we partner with them. And the question is then, how do you connect all of those things? And this is essentially what the R&D is about. So you need an ecosystem that accommodates for this, such to be able to tear all this down if it didn't prove, the correct way of doing it. Right? This is a very important one aspect. So this is why I say these prerequisites need to be in place in order to do proper machine learning, also experimentation, but also scaling later on. So back to that particular example here. The question is, of course, could we actually, from an optical point of view, classify whether fabric is faulty or not? Usually, for manual quality control in the past, before the automation was in place, what factory workers do then is that they actually look at that fabric and then shine a particular color of light on that particular fabric, and that somehow intensifies certain aspects of that fabric. If you look at a piece of fabric, again, red or green or blue, there are different aspects you're able to detect from optical point of view, right? Of course, they also, as I said, they also do from a haptic point of view. But the question is, can this just be done by just looking at the color, the best shiny color on a particular fabric? So we tried to do so. So all the data that we had from the Raspberry Pi, we actually have been shining 3 color of lights against those pieces of fabric. And in the middle piece here, the baseline, you see various examples of fabric, which is the baseline. So that means that's okay fabric. And below you see defects against various colors, right? So we did not want to rely on anything called deep learning, artificial neural networks per se. There has been a lot of momentum there the last few years, but we thought it was kind of overkill. So if you look at just the histogram, basically the distribution of colors for all those baselines, this seems to be different from the histogram, or basically the distribution of colors of the defects. So if you just focus on the one here that's red here, you see we have 1, 2, 3, 4, 5, 6 samples, and the distribution looks like this. That's the distribution of red. But for the faulty one, so this is one here in the middle down there, the defects actually also give rise to a different distribution. So just by comparing these two distributions without relying on deep learning anything, we say there is probably enough to say there is a defect, right? So this is a very nice example where it might be overkill, and this is actually what we found out during R&D phase, where it's overkill to use deep learning or anything similar. What is what you see here 2 defects, and you see the particular defect, which is somehow, depicted here by the vertical line here, gives rise to a certain dip in the middle. So that just means if you compare 2 distributions, you can say, okay, if it looks like this, it's a defect. If it looks differently, so if it looks like that, so one of those 6 here, examples here, then it's okay. And actually 85% accuracy we were able to obtain based on that. So it was hardly anything to do with machine learning and artificial intelligence, but just being very, iterative and R&D aligned during the process of developing this, we figured that out. So this is one example. Another example is from Tower Semiconductor. Here I can name the company because we actually we no longer on NDA with those. It was about wafer quality control. Wafers, I'm not sure you know what that is. That's basically the semiconductor material, silicon wafer semiconductor material that is the foundation of computer chips. That's what you see to the left. And using photolithography, you are able to actually imprint the various subcomponents of a computer chip, resistors and capacitors and the like, right? And of course, this is very, 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 this is quite error prone because we are talking, sub millimeter level here, obviously. And it's of course quite dramatic if one of those chips end up in a computer and it's faulty. So quality control is really, 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 really important. Most production facilities already have some kind of quality control into place, but they do not have the machine intelligence to actually detect with a certain high accuracy that this is actually faulty or not. They basically just take a picture, and what the company that owns those production facility does with those pictures is up to them, right? So the question or the challenge is basically to automate the quality control from high-res pictures, such that we reduce downstream surprises later on, obviously, such that it doesn't end up with computers, and to improve upon the existing system, which was really, really crude, was done more or less manually. The approach was here to use, again, SageMaker machine learning on Amazon Web Services, but also to figure out if we can use a low-code or no-code approach for this. So without actually doing a lot of research and development, without having a data scientist on board. So this is how the pictures look. Actually, there are 5 classes, just to give you an example. So on top, these are all fine. The 3 below, they're all bad. From optical, just from my perspective, there is hardly, you cannot really distinguish why there should be an error or not. So the question is, of course, yeah, you can go about this with deep learning. We also did so, but that's not the point here. We, as I said, try to use a low-code, no-code approach to go about this. So basically, without having a data scientist involved here, data scientists would be involved in the middle layer here. This is basically the machine learning AI stack on Amazon Web Services. You have the middle layer there. That's basically a full-fledged integrated development environment where data scientists usually, will do the analytics, the R&D in an iterative fashion. But at the very top there, you also have these low and no code aspects from Amazon Web Services, where you have a very clear API. You don't need to be an expert And a lot of those services on top there have, of course, have come about from Amazon Retail, and they also offer those. They now offer those services, you know, for general consumption and Amazon Web Services. I will jump this here. Of course, with deep learning, there are certain. I mean, if you work in this SageMaker layer there and you do your data science there, we try to do that as well. You will see a significant improvement using deep learning. Based on you know, standard architectures. Basically, it says here that anything that is in the past predicted as good was actually very, very faulty. This is existing. So 21% of those examples that passed were actually absolutely not good, right? Reduce that to 0.02. So with deep learning, we managed to do so. The question is now, can we do that same with a no-code, with a low-code or no-code? Which makes life much easier. You don't engage data scientists. And this is where we use Lookout for Vision, which is such a low no-code environment, which is basically kind of a software as a solution service, very high level. And there's a GUI for this. You can also use it from an SDK or from an API, REST API for that matter. So the way that looks at, you basically upload anything, all your examples, in this case, all those examples, of course, were already available because the production line had all those pictures already taken. So we just uploaded those, what you see here, and we then can then basically say, this is normal or non-normal. We did that for a lot of those examples, and then you basically just press train model, and what goes on in the background, you don't need to care about, right? So this is basically Amazon's, you know, headache to make this work. You know, and you don't need necessarily to know anything about deep learning and so on, right? And then you can go ahead and, of course, check the performance on a test set using cross-validation, and you actually get something that's very similar to what you would get if you'd be a data scientist and work in the SageMaker layer instead. So instead of having that explicit expertise and coding expertise, this low-code, no-code solution actually does exactly the same. Of course, from here, it's just a question of then putting it into production. Very easy. So this is the low code, no code, very easy. The pictures were already there. I think this whole engagement took like a month or less. And you get a clear endpoint at which you then can test your models. So this is just basically just sketches you basically two use cases in manufacturing realm. Of course, as I said, there are many other opportunities as well. At AllCloud, we, as I say, we are not only about innovation, machine learning, AI, but nevertheless, those service offerings is what you see here. Of course, we do data pipelines, data analytics and BI, data access frameworks, but we also do data operations. So for instance, what you just saw, Lookout for Vision, we will also make sure that it will work in production when we leave, once we leave such a POC or such an engagement. So we basically take care of it end to end for you. If there are any questions, please reach out to me. You see my email down below there. We are hiring extremely at an extreme level. So please, if you have some data affinity or cloud affinity, please reach out to me. And as I said, if there are any questions, you can also just email me on this address. Thank you very much.
Thank you very much, Carsten, also for the call for talents. It was a pleasure to have you here today.